Hello everyone, I'm really happy to see all of you in this beautiful city of Miami. So my name is Alexey and I'm going to represent Nozomi Networks company today, one of leaders in OT and IoT space. And my role is threat intelligence manager, so I'm leading the TI team who is responsible for all types of malware-related operations, including detections, research, extending our own infrastructure. And today I'm here to present something a little bit more technical, just to show the capabilities of our team. And in the end, I will be happy to answer all the questions related to this particular operations. If you have any more questions, we will be available at the Cabana sessions later, where you can get more insights into our rich products portfolio. So first of all, when I started my career, everything was focused around Windows. Yeah, Windows. This is a great, very versatile system, which all of us are very well aware of. It's great for everyone, for teenagers playing video games, for financial specialists doing banking transactions, and of course it's widely used in OT space as well, for example, as HMI. And when we are talking about OT, IT, and IoT, particularly in terms of detections, the border between them becomes really blurry. So let's think about HMI. Yeah, it's a Windows-based machine. It can be affected by Stuxnet, which is perfectly aware of what OT is and how to take advantage of it. And it can also be affected by some banking software, which is completely unrelated to OT and may not actually possess a real threat to the company, where it may end up in HMI device, for example. So same applies to IoT. Yeah, some cameras may be used to monitor the operational manufacturing process, and whether they're affected by IoT threat or not, it's up to reverse engineers to tell exactly what are malware capabilities, what attackers can achieve, and what is their motivation. So, and when we talk about IoT malware, they share lots of counterparts with their Windows-based colleagues. So, when we talk about IoT malware, most of them are based on Linux operating system, Mirai, Qbot, and many others. So, and one of the things that they share is attempting to evade detection. There are multiple names how this process can be known under. It can be anti-reverse engineering, it can be anti-debugging, which is actually a subset of it. So, but basically the idea is the same. They are going to prolongate the infection process as long as possible in order to maximize the gains. For some of malware categories, it's less applicable. So for example, for ransomware, as long as they hit the system and they affect the file, it's done. They don't care anymore how long they can be there. It may be more important, for example, during the lateral movement, when they propagate across the network and try to get as many systems as possible, whether it's IT, OT, or any other sector. For attackers, it may not necessarily be matter as long as enough systems is being affected. So today I'm going to present a research done by our threat intelligence team, again, just to show some of our capabilities and insights into IoT space. So here in particular, we're going to focus on packing techniques. What is packing? So for some of you who may not necessarily have a reverse engineering background, there are various ways how malware can try to evade the detection. They may encrypt certain important pieces of data, strings, configurations, pieces of code. They may apply techniques like obfuscation, anti-debugging to interfere with the debugger attached. Packing, it's a more universal term. Generally, it is being used when we're talking about big blocks of code and data being compressed in most cases, but sometimes it can be only encrypted. And this is how malware protects itself. So your existing signature-based solutions may fail to detect it as long as the sample is new. So existing IOCs don't work for them, and the actual code and data are not available. And you can't detect a threat by detecting packed code. It's just a high entropy, random-looking block. The unpacking code is standard if a well-known legitimate product is being used to perform it, so you have a problem unless you are able to unpack it and see exactly what's going on, what's the actual functionality of the thread. So here in this research, we're going to explore the current status of packers used in the wild by IoT malware, what's the landscape, what attackers are being used, where we are now, basically. The research has been done using the chain of Nozomi networks IoT Honeypots, which are spread around the globe, various sensors, from where we are collecting data from, and we also have a dedicated system to aggregate it, enrich the data, and use it for research, for generating automatic detections, for sharing with partners, for all possible needs, basically. And in the end, I'm going to cover a few techniques of how unpackers for IoT space can be approached in general. There are lots of resources how to do it for Windows-based threads, but there are very little to known universal approaches for IoT space. So this is what I'm going to present today to you. So IoT honeypots, basically, as I'm sure most of you know, honeypots are just vulnerable systems that aim at being hacked. They aim at emulate certain functionality which attackers may be interested in, and the data which we collect there can be used for all types of cybersecurity purposes, including detections, research, and creating new defenses. So what we did is, over a particular period of time, we collected data across all different sensors, emulating various vulnerable protocols. The top ones in IoT are still SSH and Telnet, which were popularized by Mirai, obviously, but we also maintained a few others, obviously. And over the course of 7 days period, we collected more than 200 unique samples from various attacking attempts. As you can see on this diagram, most of them were actually ELF binaries. ELF is the most common format in the Unix and Linux world, and 32-bit operating system is still the most widely used. The actual architecture varies. So ELF files can be used for x86, both 32 and 64-bit, for ARM, MIPS, Spark, PowerPC, Motorola 68K. The actual architecture doesn't matter. It will affect the instruction set used by produced by compiler, but the actual format will be the same, ELF. So, and as you can see, the vast majority was actually for ELF 32-bit. When we started looking at packing methods, approximately 1/3 of them was packed with UPX. There is no surprise. UPX is the most widely known open source packer, which is widely used by most legitimate companies just to reduce the size of distributed binaries, and malicious actors as well. So, and actually, still, after all these years, UPX was the only one known packer that has been used by all types of actors. When we're talking about Mirai, for example, they not necessarily, the attackers, the people who distribute it, may not necessarily apply packing techniques in general to protect their brain children. So, for example, in case of original Mirai, the simple XOR encryption was applied against credentials, which were very easy to spot and detect the threat. Apart from that, there were a few other techniques, like using ptrace to interfere with debugging. We don't call it packing. When we talk about packing, it's a particular term, and here UPX was only one kind of actor. It makes sense because the market of open source packers is unfortunately still very limited, and UPX is probably one of very few solutions available to general public to protect their programs. Another reason is purpose of original protectors. They were created for copyright reasons, so that game developers, paid software developers can protect their products against piracy. In open source, it doesn't make much sense. In many cases, open source is distributed for free, so there is nothing to protect in this case. What we did after that, we looked at the set of samples we collected, and we looked at all the samples which were not present and not detected on VirusTotal. VirusTotal is a shared website where everybody can see how many various detection engines detected a particular sample. We were interested in something which the community didn't know about before, or they knew about, but they didn't think it's a threat until we started looking at it. And in this case, this subset of files shared very similar percentage distribution. Slightly less, not 1/3, but 1/4 of them was again packed with the UPX. UPX is well known. It's open source, and it provides actually a tool to both compress and decompress the payloads. And obviously, for attackers, it's far from ideal. If everybody can immediately decompress the payload, there is no point in actually putting an extra effort. That's why attackers generally apply certain additional techniques in order to complicate the analysis, complicate the unpacking. And usually, what they do, they apply certain modifications to the result sample structure in order to prevent their original UPX tool from unpacking it. In most cases, IoT sample apply very particular modifications, which will make the sample executable still. It will not affect the actual functionality, but the UPX itself will treat it as a foreign sample and will refuse to unpack it. There are two particular structures that have been used so far, which is p-info and l-info. Both of them can be found in the source code of UPX for L files, and different malware families tend to apply different modifications for these structures in the result samples in order to prevent samples from being unpacked. The classic one is changing the L magic value of L info structure. It's a hard-coded signature, UPX exclamation mark. If you overwrite it with anything, UPX will stop recognizing it, but the sample remains perfectly executable. This is what most attackers do. For example, SB Diet, which is the one that we analyzed a few months ago, is famous for using this technique. Mozi, another example of IoT threats, follows different strategy. So it targets the p-info structure, and it changes the file size and block size of the values. It changes to 0. UPX thinks it doesn't have enough information to unpack it, which is not exactly true. Even though it refuses to unpack it, the sample remains perfectly executable, and the unpacking code, which now comprises part of their packed sample, works perfectly fine. Which also means that researchers can follow the steps that unpacking code follows and unpack the sample manually. But they need to know how to do it. During that research, we accidentally encountered a new challenge. Basically, when we applied UPX-D in order to see if it's a problem with L-info or P-info file, UPX suddenly told us, oh, I have a new problem now. The problem is with B-info structure, which is very uncommon. B-info structure, it's placed before each compressed block, and similar to other structures, it can place additional information for unpacking code, how to handle it. In this particular case, it contains information about unpacked size, the algorithms which was used for compressing, and various parameters. Parameters are generally used to achieve a particular balance between performance and size of the result payload. We took a look at the B infrastructure, and there was nothing obvious. It wasn't just nullified or modified in some clear way. So first theory that we had is that the difference between compressed size and uncompressed size is something that interferes with the unpacking process and prevents us from easily unpack it. We checked, the values were coherent, so nothing clear in this case, so we moved on. Another challenge was the checksum. So checksum obviously is being used to prevent very obvious small accidental changes in the code or data, which would be noticed with a high probability. The smaller the checksum, the higher probability of collision, so it may not necessarily be 100% bulletproof, but in many cases it works. And in our case, the algorithm was there. It's open source, so we could calculate it and check if it's valid or not, but it would require additional work, so we temporarily stopped following this direction and decided to explore other ways, how this can be approached. What we decided to do, we decided to take a look at what parameters were used to generate this particular sample, try to simulate them and generate as much simple as possible, but which will follow exactly the same kind of logic. It will follow the same structure and compare the results. Sample which we're trying to unpack and the new one. UPX provides kind of command line arguments that will allowed us to see with a more or less higher kind of accuracy what were the arguments used to create the packed sample, and we generated the similar one. Compared them, we immediately spotted something which we didn't see very often before, the version of UPX. The latest version of UPX has been 3.96 for more than 2 years now. This is the latest production build. All researchers in the world, okay, 99% of researchers in the world are using the latest build because it's backward compatible. Everything that was packed with all previous versions of UPX could be unpacked with the latest one. However, for this sample, it wasn't the case. So as you see here on the screenshot, this sample was packed with a version UPX of 4.0, which is still under development. It's not available in the release. It's unstable. When I tried to use it 1 year ago, for example, it failed to produce a valid binary, even though it told me it's perfectly fine. So it's still in early stages of development. And apparently for attackers, it worked. So they took their test build, which is not ready for production. They used it to protect their brainchild, and luckily to them, not for us, it remained executable. So, and in this case, once we figure out the logic, we explored the kind of situation what's going on, and actually the problem was again with well-known L-info structure. So after fixing their existing magic, which we knew before, everything worked perfectly, and the sample was unpacked, which led us to a new kind of area for many people, how to manually unpack IoT malware. Doing such research is fun if you have plenty of time, which we may not always have. Some new threats hit the news. We need the results now, preferably yesterday. So we need to unpack sample quickly and get answers, what it does, what are the capabilities, what will be the impact, how to remediate it, who was behind the attack, and so on and so forth. And regardless of what packers IoT malware developers use, whether it's UPX, whether it's something custom, well, it will be something that will appear in the future, tomorrow, 1 year later. It's always possible to unpack it in the debugger, just because the unpacking should happen before the actual functionality will be executed. Basically, in most cases, it doesn't matter what you unpack, whether it's Windows samples, MZP, file structure, or Linux ones. Exactly the same steps should be followed by the unpacking code. And this is something that we can exploit. Our goal is to stop at the moment when the sample is already unpacked but hasn't been executed. Why? Because obviously at this moment, all code, all data is already present in memory, but it hasn't been modified during the actual operation. So this is a perfect spot to dump it on the disk and continue the analysis. Reverse engineers call this spot, the first instruction, which is going to be executed, is original entry point. So entry point is something where the execution generally starts, in absolute majority of cases, with certain exceptions. And this is original entry point, the entry point of the original sample before it was packed. So technique number 1. All these techniques are based on the workflow of unpacking code, which it has to follow in order to unpack the sample. And again, this is something that we are going to exploit. First step that it has to do is that packed code and data should be read in order to be unpacked. So the sample should read its own body to read the compressed or encrypted or both code and data before it can be processed. And this packed code and data is visible. It's visible with naked eye with proper tools have been used. So here, for example, in the screenshot, you can see a representation of packed code and data in my favorite tool. It's called Hue, Hacker's View. So here you can immediately spot the high entropy. What does it mean? Generally, in code and data, 0 is the most prevalent symbol. Same as in various human alphabets, like in English, for example. Certain letters are more prevalent than others. Yeah? Same applies to binary code and data. In this case, 0 byte is the most obvious one, the most commonly used. And this particular tool is representing it with a particular symbol, which is a lack of anything. It's a dark spot. Here you can see the number of dark spots is very little, which means that the randomness, the entropy level of this particular area is very high, which is a perfect kind of indicator that this code and data are packed. What we can do after this, we can just follow cross-references. We can search for all places within the code where this block is being accessed and follow them to find the unpacking routine. As long as we found it, we just need to go to the end of it, and the sample is unpacked. Second step, big memory block should be allocated for the result. Once this code and data are unpacked, they should be placed somewhere. There should be space for it prepared. And memory allocation is one of the most common ways how additional memory can be dynamically achieved. On Windows platform, usually virtual alloc X, and so on, are used for these purposes, apart from heap. On Linux systems, syscall mmmap is used to allocate memory. There are other ways how it can be achieved. For example, with UPX, when we talk about UPX on Windows, they use different strategy. They are creating empty section, which is not physically present on a disk. It will be only present in memory, but it will have no physical representation. And later, this area in memory will be populated with code and data. The result is the same. As long as we found this big block, we can put a breakpoint when something will be written there. And as long as the data, unpacked code and data starts being written, we just need to wait until it finishes. We will get both of them available. Third step, result of the unpacking code should be written there. And here where different types of breakpoints become handy. So to give you some idea about what breakpoints is, breakpoint is a term used in the debugging where we put a marker and we want to stop at this particular place in the code, in most cases. Whether this instruction is being executed, it's the most common case, they're called software breakpoints, or some data is being modified. Usually, for this purpose, memory breakpoints are being used, and there is a separate category of breakpoints called hardware breakpoints. They're implemented differently behind the scenes. They use particular registers of the CPU, but the result will be the same. They can be used to stop either when a particular instruction is being executed or when particular data is being accessed or modified somehow. And again, same story, as long as we know that in this particular place something will be written, in our case unpacked code and data, we can put these types of breakpoints, intercept the moment when it starts to be unpacked, go to the end of this process, and we're fully set. One more step, execution protection flags. So memory, when I talk about memory, I'm talking about random access memory, RAM. So right now, we went away from using segments in memory. In most cases, for x86, for example, the memory is flat. And we have particular memory ranges in order to store code and data, resources, everything. To differentiate between them, because for CPU, there is no difference between code and data. It's just number of bytes. The bytes are the same, from 00 to 255, or FF in hexadecimal. To add some additional layer of protection, the memory protection flags have been invented. What it is, it's a particular marker which says whether this particular memory range is readable, executable, or writable, or some combination of them. And unpacker needs to change them occasionally. For example, when the code is unpacked to a newly allocated memory, it needs to be marked as executable. Otherwise, in ideal world, in most cases, the system is supposed to refuse to do it. It hasn't been enforced, for example, on Windows for many years. Only later they introduced DEP data execution protection or prevention to protect only a particular kind of process. But for backward compatibility, it couldn't be done straight away. And here, the logic is exactly the same. We're monitoring the syscall, which is responsible for changing memory flags and protect. And as long as it has been executed, we can check what exactly has changed, whether some particular memory range became executable, or whether the modified ELF header became non-writable again. All these steps are something worth monitoring in order to intercept the moment when code and data are already unpacked, to stop at the entry point. Finally, the control should be transferred. So once the unpacking is done, the CPU should start executing the newly fresh unpacked malware from the original entry point. And usually, it's not very easy for unpacker to know exactly where it will end up. So in many cases, there will be particular instructions which provide certain flexibility. For example, the final address where the code should go will be stored not in the hard-coded form, but in a register. The register is a particular special unit of CPU which can store various types of information depending on the bitness. So usually it's either 32-bit or 64-bit on modern CPUs. And here, as you can see in the last instruction, is jump to a particular address which is not known. The address is encoded using a register. And this is a strong indicator that this may be a transferring control to the original entry point. There will be very few of them in the unpacked code, and finding all of them, in most cases, guarantees the moment when the code and data are unpacked. And finally, a bonus tip for UPX in particular, there is a syscall memory unmap, munmap, which has been executed just a few steps before passing control to the original entry point. Again, this is a very low-hanging fruit which researchers can use in order to stop at this particular moment, execute a few instructions, and you are stopping at the original entry point where unpacked code and data are available for your analysis to understand malware functionality and perform any type of cybersecurity kind of activity which you may be interested in. And that was basically it. So thank you very much. Again, these are some of the capabilities of our threat intelligence team, which is one of the products that Nozomi Networks provides. So if you're interested in getting more information, please contact me. Or if you're interested in Nozomi Networks products in general, please join us at the Cabana session today. So thank you very much.